Hello, and in this video we're going to look at power and polynomial functions. We're going to define a power function. We're going to define a polynomial function. We're going to look at what these are: coefficients, leading coefficient, term, leading term, degree of the polynomial. All that has to do with polynomials. And we're going to look at long-run behavior and short-run behavior of power functions and polynomials. So let's get started with power functions. A power function is a function that's defined as a single term with just some base that's a variable and some power that's a number. Some of our tool kit functions that we've used already are power functions. Even linear functions are power functions. So it could be any power whatsoever. You could have this as a fractional power. So f of x equals the square root of x is a power function because that's x to the 1/2 power. It can be defined as x to the 1/2 power, and that's a power function. But if we're just looking at some of these even and odd power functions, they have some characteristics that are pretty common. So all even power functions are symmetric on the y-axis. They go through 0, 0. All power functions actually go through 0, 0. Every power function there is goes through the origin 0, 0. All even power functions like this, they also go through points 1, 1 and -1, 1. All even power 1, so x to the 4th would do the same, x to the 6th would do the same, x to the 10th power would do the same. What happens is if the higher the power, the flatter it becomes close to the axis here and goes up faster like this. So if it turns and it's flatter here and then turns up faster, then that's a higher power. This might be x to the 6th power. So it turns as flatter and then it goes like this. All even power functions look like that. Now odd power functions have a similar property. They all go through the origin, 0, 0. They also go through the point 1, 1. And they go through the point -1, -1. Down here, -1, -1. So all odd power functions look like this. If they have larger powers, they do the same thing. They're closer to the axis to here, and then they go up, shoot up faster. So they're closer to the axis here and shoot up faster, but they still go through those points. This would be something like x to the 9th power, some odd power. Okay, some odd power, some even power. Okay, now when we look at these, we're going to be looking at some of the end run behavior. We're going to come back to that after we define what that is. But that's how even and odd power functions look, and they have similar properties here. Okay, we're going to move on to polynomials. A polynomial is a function with a sum of terms that are transformed by power functions with positive whole number powers. So the powers here are positive whole numbers. Here's a power here that I didn't put. Okay, so this right here is a polynomial. Its coefficients are the numbers that transform each power function. So the coefficient on this term is equal to -3. Coefficient on this term is equal to 2. Coefficient on this term is -10. This is a constant, so it doesn't have a coefficient and a variable. The variable coefficients have a power function, and this one has a power function, but this is, if we rewrote this as a power function, this is 5x to the 0 power. So 5x to the 0 power is 5, and 5 could be considered a coefficient. Now the leading coefficient is the number that has the power that's the largest. So this right here is the leading coefficient. Even though it's not written in the right order, this is the leading coefficient because 5 is your highest power. Now the terms, we have 1, 2, 3, 4 terms here. They're separated by minuses and pluses. So there's 4 terms here in this polynomial. And the lead term is the term with the largest power. So the lead coefficient and the lead term are connected. So negative 10 x to the 5th is lead term. And the degree of the polynomial is the power that's on the polynomial. So the degree of this polynomial equals 5, because that's the power, the largest power in all of these. We got 1, 2, 5, and 0 as our degrees. Now, usually we don't write our polynomial in this order. We usually write it in descending order of power. So normally you would see this function written this way, 10x to the 5th, because that's the highest power. The next highest power is 2x to the 2nd. The next highest power is negative 3x, and the lowest power is the constant 5. So this is how we would normally write this in descending power. Okay, so you need to be able to identify all those possible things in a polynomial. And you need to know that a polynomial doesn't have fractional numbers here. It doesn't, or in powers. The powers, positive whole number powers. Powers have to be that in order for it to be a polynomial. You can't put a fraction as the power. You can put a fraction as the coefficient, but you can't use the fraction as the power. All right, moving on to long run and short run behavior. Now, long run behavior is what happens to the function or the y values of the function as x values get large when they go to positive and negative infinity. The short run behavior is what happens near the center of the graph, the horizontal and vertical intercepts and the local max and mins, which they also call those turning points. Turning points are the max and mins. Now, in short run behavior, horizontal intercepts are called roots or zeros. And an nth degree polynomial will have at most n roots and n minus 1 turning points. So if we look at this example of what's the long run behavior on something like this, we would need to look at its lead term. This has at most 5 roots, at most 5 roots or zeros, and at most 4 turning points. That means it has at most 4 max and min points, local max and min points. We don't know what exactly it looks like, but it has that. Now, long run behavior is based upon the lead term, because that affects it the most as it gets big. And we're looking at what happens at infinity. So at infinity, this power is going to be much larger than these down here. So this is going to affect the long run behavior. So it's going to look something like this. Now this is a x to the 5th power. And if we go back to this, it's an odd power, so it's going to look like this red graph here, moved around a little bit. So x to the 5th power is going to somewhat look like this function right here, but it's going to have some turning points in it. And it's going to go up. So 1, 2, 3, 4. I put 4 turning points in that one because it's what it has. So it's going to look something like that at most. So, and it's going to go up because of the 6. 6 is positive. If it was negative, it would go down. So the long run behavior here is basically saying as x gets big, goes to infinity, means we're going this way. We're also going this way, so that means the function approaches infinity, goes up. And as x approaches negative infinity, that means we're going this way, negative infinity, then we're going down. So function approaches negative infinity. So long-run behavior is usually going to either go to infinity if it's going up forever or down forever, like these. Okay, so on these ones with long-run behavior, as x goes to infinity, f of x, that's the function, goes to infinity. That means it's going up as it goes to the right. And as x goes to negative infinity, that means it's going left. It's also going up to the left, so the function is going to go to infinity both ways. It goes up both ways as we go right and left. This is just saying go right. This is saying go left. So as x goes to infinity, or go right on this, we're going to go up. As x approaches negative infinity, that means we're going to the left. Then the function goes down. It's going down as we go to the left. Alright, so the only changes happen to these two power functions if we put a negative sign on it. So if we put a negative sign on it, if we go negative x squared as our power function, then what happens is it goes like this. Because this negative number means that we have to transform it to be a reflection on the x-axis. That's what a negative does. So it does this. So both of these are going to say f of x is going to go to negative infinity as we go right and left. We go right and left, we go to negative infinity. Now, on these odd ones over here, if we go negative x to the third, that's still a reflection on the x-axis. What's going to happen is it's going to look like this. It's going to reflect. This normal piece down here would reflect up here, and this piece that was up here normally would reflect down there. So that means it's going to reverse these two things on our long-run behavior. So on this one, x approaching infinity means the function approaches negative infinity. And x approaching negative infinity means f of x is going to approach infinity. Let's look at the graph. So if we go this way, it's going to go up to infinity. If we go this way, it's going to go down to negative infinity. That's what we're saying there. Now, that going back to polynomials, we're going to look at the lead term, and we're going to look at this lead term, and that's going to determine what it's going to do. All right. So this one's going up from left to right, and so we have this long-run behavior. All right. Now, let's look at this one right here. This says find the vertical and horizontal intercepts of this function. Now, vertical and horizontal intercepts happen when 0 is x and when 0 is y. Okay, so this one should be easy to do because we're just going to put in f of 0 for this one. So we just put in the 0 here, so this is going to be 0 plus 1, this is going to be 0 minus 4, and this is going to be 0 plus 5, and we're going to figure this out. So this is 3 times 1 times negative 4 times 5. So 20 times 3 is negative 60. So this is negative 60 for the vertical intercept. This is the vertical intercept. Now the horizontal intercepts are going to happen when each of these equals 0. So we have 0 equals 3 x plus 1, x minus 4, and x plus 5. So when each of these things that are multiplied together equals 0, so this could be 0, the whole thing is 0, this could be 0, this could be 0. So there are actually 3 different horizontal intercepts here. The 3 horizontal intercepts are -1, 0, because -1 plus 1 is 0, 4, 0, because 4 minus 4 is 0, and -5, 0. And that would be because -5 plus 5 is 0. Okay. Now I want to do one more thing. I want to take a look at some graphs and see if we can figure out what the polynomial would look like. So we basically touched on this one by knowing what this one is, but we're going to look at some graphs. Let me draw some graphs. We're going to look at some of those graphs. So if a graph looks like this, okay, this has 1, 2, 3, 4 turning points. That means it has to be x plus, or it's x minus 1 equals 4 for this one. For the number of turning points, remember we said x minus 1 equals the number of turning points, so x equals 5. That means the degree of this is 5. So this is x to the 5th power, but it is going down, so this has got to be a negative x to the 5th power. Alright, so this is a negative x to the 5th power function. This is the least possible degree. It could be more than 5, but that's the least possible degree. Now if I do this, and I draw it this way, there's 1, 2, 3 turning points. So 3 turning points equals, it's actually n minus 1, not x minus 1. So, made a mistake there. This is n. Number of turning points. So n is 4 here. So the number of turning points, this is x to the 4th. And it's positive because it's going up. Positive x to the 4th. Okay? So you should be able to count by the number of turning points what degree it is. Alright? Okay, so that's the power and polynomial functions. We talked about all of these things. Short run behavior is the intercepts and the turning points. Long run behavior is what happens when x and y go to, or what happens to y when x goes to the right and left. And these all are parts of polynomials, and a power function is how we build polynomials. So that's that section.